Okay, our next speaker is Moshe Tanach. He's the CEO and founder of New Reality. Uh, Before founding New Reality, he served as director of engineering at Marvell and Intel, leading complex wireless and networking products to mass production. Welcome to the stage.
Thank you. Pleasure to be here. Think it's working? No. Excuse me 1 second. Okay. Okay. Welcome, everyone. Thanks for coming. I'll have a poll to begin. How many software engineers are there? How many hardware engineers are here? Oh, thanks for coming. How many finance, operation, management? Okay, now I know my audience. So today I'm going to talk to you about affordable intelligence for profitable growth. I don't know how many of the software, hardware engineers care about profitable growth, but I guess a lot of the finance and operation and the people that sits on the P&L do. And we live in an amazing era. The AI era, the amount of innovation, research, new type of architectural changes for neural net models, mixture of experts, all kind of new use case from ChatGPT to content creation. And the amount of innovation on the hardware level is also quite amazing. We're moving to 700-watt GPUs, huge racks and superpods, supercomputers driving all these new capabilities. But yet, when you look forward, the big market is really in inference, in using the AI models that were trained, the AI pipelines that we deploy. It's not only for research. And right now, research is pulling a lot of the investment, a lot of the cost that we're spending. But eventually, everyone wants to take advantage of those AI. And it's anticipated to be at least 8 times the size of training models. Today, besides all this amazing innovation, it seems like we're hitting a wall. And if you look on the last few weeks, the amount of pressure around the cost, about the power consumption that many companies, you probably heard about Microsoft and Google chasing nuclear power plants, and how do we feed all the power to those huge supercomputers? And today I want to talk to you about the other side of taking those trained models that are using those supercomputers, and how can we deploy them in a more affordable way, so we can really deploy them in every line of business, even in smart cities that they don't have the amount of budget that Meta or Google or Microsoft have. But I'll start with a bet. If I would ask you which of these cars will get it to the mountain, the first mountain stop first, who would you bet on? I guess you want to know what's the size of the engine, who's driving, what's the traction system, etc. Now, if I would ask you who would come first, would you care about the size of the engine? Well, actually, when we're looking on what's going on in data centers today, and the amazing H100, B100 from NVIDIA, the MI300 GPU from AMD, and the other TPU V5, V6 that are coming, it's kind of the same problem. We're making the AI processor, the AI accelerator, stronger and bigger, but no one is adopting the interconnect to it, the system around it, and making sure that we can deploy models in a more efficient way. So we're actually ending up wasting a lot of the cost and the power that we invested. And you know, with every technology, the success of a technology is when it becomes ubiquitous. And ubiquity usually comes when you can afford it, when many market segments can afford that. And when you look on how we can get to the point where the cost of million tokens drops from 25 cents to less than a cent, You need to consider the cost of the infrastructure, the cost of the software layers above it, user experience, that is many times pulling a lot of investment that 7-Eleven R&D center doesn't have. You have the real estate issue. You know, the new Blackwell rack that Jensen announced about 4 months ago consumed 140 kilowatts. When you look into some of the biggest data centers that Bank of America have, or JP Morgan or other companies, they have power supply of 13 kilowatt, or 15 or 18 to each rack. You cannot buy this and install it. So we need to consider all this when we're suggesting how to solve the problem. The first thing to look at is the difference between training, the process of teaching a neural network or a set of neural networks in a pipeline to classify an image, to do a multimodality embedding and understanding. And it's usually a long process, and where the spending is the R&D spending. This is not something that is directly attached to the cost of our product. When you look on inference, this is something you do on a daily basis. You want to update it on a daily basis. You want to deploy fast. You want the cost to be very low. And the attention and the innovation that you drive into training is what's leading everything. With inference, it's how fast I can deploy and how much value, how much ROI can I get on it. These different drivers go to the purpose, of course. The purpose of training is to drive innovation. The purpose of inference is to run data center operation to support my business in terms of budget, R&D spending versus my cost of sale. In terms of computation, I want to train my models the fastest I can. So I'll use the biggest supercomputer that will finish this job fast and have my PhDs go to the next iteration of improvement. With inference, I want to use the lowest cost infrastructure that I can, embedded if possible, or data center if possible. The precision is different. With training, we're using high precision, 64-bit, floating point, 32. With the inference, we sometimes drop to integer 8, integer 4. We already have some deployed inference running in 1 bit of precision. And it goes on and on and on. And when you define where you want to take your infrastructure, you need to understand the differences between training and between inference so you can adopt your infrastructure for inference. Another thing that needs to be considered is we started with monolithic general purpose compute. What is it? We're using plain vanilla servers with or without GPUs, and we're loading all our application and AI acceleration on one server in a rack. When you think about efficiency, usually there's no perfect balance inside an application that you design. The balance between how much CPU power you need and how much GPU. So you're always wasting silicon. The way to better use your silicon is to move to a disaggregated solution. Now I have my application running on plain vanilla server on the left, and when they need to offload an AI pipeline computation, they will send it to a remote server that is purpose-built for inference. So I load all my GPUs on the right, and I'll use plain vanilla servers to run my application on the left. And the connection will be with network. And now we have very fast network. We can even go to InfiniBand and Rocky V2 in order to accelerate the network. So the latency is not such a big deal. And the fact that you aggregate the AI computation on one side and the general purpose on the different side allows you to scale better and not to waste your silicon. When you're stretching it further, and this is what we do in New Reality, we actually take the system architecture of the right server, of the AI appliance, and we build it from the ground up to be ultra efficient. And this is why I want to show you today what we're doing and what you guys need to start thinking about when you're leveraging AI infrastructure, hardware or software. So I'll start from how inference servers are built today. We call it a CPU-centric architecture because the CPU in the center, the Intel AMD device, is the piece that is running your AI server application. Or if you're using NVIDIA tools, you're probably running a Triton server that is hosting the GPUs and is ready for provisioning of models and for queries coming in and response going out. The problem with that architecture is that there's a bottleneck created in the CPU because it needs to do a set of things from network termination. It gets all the Ethernet packets. It needs to reconstruct the data, whether it's an image or an audio or whatever. And then it needs to run some quality of service. This server is serving hundreds, maybe thousands of containers sending queries. I need to do some queue management and scheduling and make sure that I don't starve anyone. And those are parallel compute nature functions, processing that the CPU is not good at. And the more queries coming in, the more bottlenecks we see there. So we ended up putting a CPU, 300 watt, maybe 400 watt worth of silicon, $10,000, but it's limiting our ability to use the GPUs. The DLA is deep learning accelerator, for anyone who wondered. A form of a DLA is a GPU. The TPU is an ASIC solution for a DLA. So what we're seeing now is actually the industry is starting to throw more hardware on the problem. Grasshopper, or the B200, is taking more CPUs on every GPU. We see them coupling one CPU with one GPU or one CPU with two GPUs. This is the wrong way to solve the problem. So what we have done, we changed the system architecture so it's more scalable. And the more GPUs you have, the more of our chips you throw to host those GPUs. And what we've done, we offloaded all the data path. This is the internal of our chip. We swallowed the NIC, the network interface controller that you buy from Broadcom or NVIDIA or Intel. We developed a hypervision layer that instead of using the CPU for quality of service, for pipeline processing, we offload it to hardware. And we have a bunch of pre-processor and post-processor, DSP-based, audio codecs, video decoders, so we can keep the GPU busy in neural net processing. This is its purpose. And do all the complementary processing that is needed without using a CPU that is a single-thread machine and not very efficient. Now, we do have CPUs inside. This device do run Linux and Kubernetes plugins to connect to your orchestration layer, but the point is when the query come in for processing, it will not go to the CPU. All the data path is in hardware, and all the management stays in software. That's the key to achieve efficiency. So this is how the server looks. It's quite different than what you use in your data centers, the one who knows how the server looks. There's no CPUs in the system. You have the front line with our cards, and in the back line, you can put any type of GPU from NVIDIA, AMD, Intel, Qualcomm. And the two first companies that we work with and collaborate on go-to-market is AMD and Qualcomm. And I'll show you some of the benefits. Okay, so let's start from the problem of the traditional CPU-centric architecture. And for that, I brought a single example. You see three lines. In the bottom, you see the amount of GPUs being used. Okay, from 1 up to 8 in this case, because this chassis holds up to 8 GPUs. In the next graph, you'll see 10, because our chassis can bear 10 of them. And the top one is just running a convolutional neural network that was trained to classify objects without any pre-processing pipeline. And you see that even when you run only the model, there's a diminishing return. You use the first GPU, you get 42 kilo frame per second. You use the second one, you get the same amount of performance. And it keeps going up to 4, but then start the diminishing return, you're losing the efficiency. So this is where you're starting to throw away cost and power consumption and not getting any return. Now, if you just add normalization to this pipeline on the pixel of the image, you drop, by the way, so we were supposed to get to 336 kilo frame per second, and we got only 190. When we start to do minimum pre-processing, we're dropping to 140, and when we run the complete pipeline, we JPEG decoding, resizing of the image, normalization, and then the convolutional neural net, and all of it is offloaded to the GPU, we're wasting a lot of the capabilities. Now I'm going to show you what happens when you plug the same GPUs or other AI accelerators into our system. So the bottom line, the green one, is the 90K frame per second that we saw instead of the 336. When we take the AI 100 from Qualcomm, a different inference device, we can scale up to 220. The capabilities of that device is 22K for a single GPU, and you see perfect linear scalability. You're not losing anything when you're scaling and adding more GPUs to your virtual private network. And then if you take the same L40S, the GPU from NVIDIA, you can even reach 420 kiloframe per second. So all this is feeding the total cost of ownership and the actual cost of the query of your deployed AI pipeline. And it's critical to increase the utilization of the GPUs and lower the system cost. These two contributors will give you better TCO from CapEx and OpEx. And I'll show you, these are the three modalities that you care about, the computer vision, audio, and natural language processing. And you see in all of them, we save up to 90% of the cost of the infrastructure you're using. So whether you're consuming a SaaS through a cloud, whether you own your own data centers, it's all coming to your bottom line. And if we zoom into another pipeline, this is automatic speech recognition. Starts from a coded audio. We decode the audio. We do some processing to reduce noise, and then we're running the speech recognition itself to generate the text. You can see that we can drop from this graph is actually putting in blue the capital expense. So this is using a 5-year amortization model of the cost of the server deployed in a data center for 5 years. And then you get to the CapEx investment that you need to make. And in purple, you see the operational expense, which is based on the power consumption and the average cost of energy across the US. And you can see that for this deployed pipeline, when you measure the cost of 1 million audio seconds that you're processing, you can drop from 43 cents to less than 5 cents. It's really changing our thinking and allow us to deploy more AI without thinking about the ROI, because we can now try more things and find the killer app that really increase the bottom line of our organization, of your organization. This is another way of looking on the OpEx and CapEx separately. The left is the audio seconds per dollar, the CapEx, and the right is audio seconds per watt. So for every joule or watt you invest, how much you get. And you can see how dramatic when you design something from the system level and you care about all the components and not just about developing the capabilities, but really deploying them in an affordable way. There's a lot we can do today with the existing GPUs and AI accelerators out there if we just change the way we think and stick to the OEM servers that exist today. So who can afford to deploy today? What if we do nothing? Then we'll keep seeing the hyperscalers and some manufacturing and biotechnology that invest a lot of R&D costs. And they will continue to lead and own most of the AI being deployed today. But the opportunity is huge. From public transportation, entertainment, content creation, insurance, we can deploy AI. AI is in a good shape today to be deployed in every market sector. But the affordability needs to come first and user experience as well. So a call for action for you. Start bridging the gap, ask tough questions to your data center guys, to your cloud providers. What are they doing to reduce silicon waste? There are some things you can probably do in software even without changing to hardware. But it is a call for the industry to start prioritizing the deployment itself, the adoption of AI that is still at 25% worldwide, and prioritize less chasing the next supercomputer and the next 20 trillion per hour model. And understand your AI economics. Start asking, what is generating more bottom line for you? What your customers need from the deployed AI that you do? What's the cost of 1 million queries that you do? When you start measuring something, it tends to improve. And to summarize, the future is dependent on multi-angle solution. It's not just a brute force race to the first mile stop. We need to think about the transportation system, about the car, about the engine, and really make everything grow at the same time. So, questions? I did. I was exercising for 2 weeks.
Okay, let's
Just joking.
let's look at the questions. So there's one question. The performance graph compare NR1S plus Qualcomm AI 100 to a CPU plus NVIDIA GPU setup. Do you have performance results that use the same GPU setup?
Yeah, we do. We test everything we do. Usually we take the AI accelerator, we put it in a regular server. We test it. Everything we test is usually hundreds of clients on regular server, sending requests over network. So many of the AI acceleration company that you know will brag about a benchmark they submitted to MLPerf when they tested the GPU or the accelerator. We don't look at this way. We have an appliance, you deploy it in the data center, and now you need to send it AI request. Everything needs to be optimized inside. So we test it first in a CPU-centric, using the off-the-shelf Triton server from NVIDIA, or whatever some customer use Kserve or other, and then we test it on the NR1S. So we always compare the same accelerator in the two systems.
So I have a follow-up question, since we have some more time. So NVIDIA will also be coming up with CPUs to work with their GPUs. How does the competitive landscape look?
So for us, it looks very good because everybody is our partner. We can work with any GPU. I think wherever NVIDIA or AMD or Intel are coupling one CPU with one GPU in a module or in a server, it's usually for training or for a large language model that you need another software layer to run. And this is the only way they can do it today. They're also focused on the hyperscalers. They're running after them to build the next superpod for them. And they only sell accelerators to enterprise customers in OEM servers. So we come with another type of chassis through the same OEMs or ODMs, and we propose you guys or everyone to just take the same accelerators and use them in our chassis. So the competitive landscape today, the brute force approach on the elephant path will just throw CPUs and GPUs on the problem. If we want to lower the cost, improve the user experience, we need to go to an appliance-based product like we do. And we need to see those accelerators being leveraged more with an AI-centric architecture versus the CPU-centric. And we'll work with everyone who wants to work with us. Currently, it's AMD and Qualcomm, but Intel, NVIDIA, and all the rest are next.
Awesome. This looks like a very promising market. So
Thank you.
Thank you very much, Moshe.
Thank you,
for
everyone.
a great talk.